All right, so we're going to look at the orthogonal projection operator. So this works as follows. If we've got a finite dimensional subspace of V, then we define the orthogonal projection of V onto that subspace. So that's this operator here. So this is a function that maps V to V. And it's defined, instead of through a formula per se, it's kind of defined by a sentence. So what we do is we take our element V that we want to apply the operator to, and then we decompose it using what we know about how U is the orthogonal direct sum of U and U perp. And then we write V as the part that's in U and the part that's in U perp. And then in order to define the projection, we just kill off the W part. So we take only the part that's in U. That's how we define the operator. Okay, so this operator has a number of properties which are very useful. So these are codified in theorem 6.55. So for a vector V in V and the projection to U operator as in the definition. And so it's worth pointing out here that anytime we talk about a projection operator, we're assuming that we're projecting to a finite dimensional subspace. So you can assume U is a subspace and that it's finite dimensional. Then let's see. So what do we know? Well, we've got a whole slew of things. First off, the operator is linear. So I wrote it above just as like a generic function. That's this notation, but it's actually linear. So that's the content of part A. Part B is that if I look at the projection to U and I restrict it to the subspace U, then it just acts as the identity. So this means that if U is in the subspace already and I apply the projection operator onto it, then nothing happens. And by the way, notice we've got capital and lowercase u's, so I'll try and be careful and always write lowercase u's like this and uppercase u's like this, including the serif here so that you can determine the two, or distinguish the two. So we have that, and then we also have that the range of the projection to U is all of U. And what else do we know? We have that the projection of U operator, if we restrict it to U perp, then we actually get the zero operator. So it kills anything in the complement of U, orthogonal complement. And then along with that, we see that the null space of the projection to U is exactly U perp. So those kind of go together. And so this numbering of the parts of this theorem is different from what's in the book, because I group a couple of those together. V minus the projection to U of V is going to be in U perp. So in fact, this is actually how you define the operator. So this one, so the projection to U perp is identity minus the projection to U. And that's one of the homework problems there somewhere. So let's see, and then we've got this one. If you apply the projection twice, it's the same as applying it once. So in other words, anything that's already in U, if you apply the projection to it, it doesn't do anything. So this is exactly analogous to the one directly above it. If you're already, because the first application of the projection operator puts you into U, and so when you apply it again, then this part says nothing new happens. So it's just like having applied it once. And this, by the way, this is the hallmark of a projection. So anything that has the property that when you square it, you have the original thing, that's what makes it a projection. And so this came up in the homework problems a couple of times in 306. Let's see. And then the last point is that the projection is a contraction, meaning it can only make vectors shorter, it can never make them longer. So this, oh, and I forgot my subscript here. But it's true for any projection. So this is saying PU is a contraction, or is contractive, whatever you like. I don't think the book uses that terminology, but it's pretty common, so you might see it in another textbook. And then our last result is that if we have an orthonormal basis for the subspace U, then the projection to U of V is V against E1 times E1 summed up through V against EM times EM. Okay, so this is the projection to the span of E1 to EM of V. In some other notation that I've used before, back when we were talking about Gram-Schmidt, and we didn't formalize the projection as an operator. But it is an operator. Okay, so let's go establish these. Now there's so many here, this video is already starting to get long. I'm just going to prove the first couple, and then we'll come back and we'll pick up the other ones in the next clip. So let's see, so for A, if we take V1 and V2 from V, we know that V looks like U direct sum U perp. And so we have the corresponding decompositions into U1 plus W1. So I made a mess of it there. Hold on, tidy. Okay, and V2 equals U2 plus W2. And so when I say corresponding decompositions, you should assume that this is the part that's in U and this is the part that's in U perp for each of those. And so now, let's see. So if we go to see what the sum looks like, then we have V1 plus V2 is U1 plus W1 plus U2 plus W2. And so all we have to do is rearrange this using commutativity and associativity of addition, and we get the part that lives in U and the part that lives in W. So by the fact that we saw that U and U perp are both subspaces, then this is the part that's in U and this is the part that's in U perp. So when I apply the operator to V1 plus V2, what do? We just extract the part that's in U. And then notice that U1 is P of V1 and U2 is P of V2. I forgot my subscripts again, like I do. So we get additivity. And then the argument for scaling is much the same. So if we do lambda V1, this is lambda U1 plus lambda W1. And again, those two parts are in U and U perp respectively. So when we do PU applied to lambda V1, this is going to be, well, we just extract, the definition is take the part that's in U, and so we get lambda U1, and then that's lambda times, and U1 is PU of V1. So we get the scaling part as well. All right, moving right along. So for part B, okay, so the fact that it's fixed, if you start in U, so this is immediate from, let's see, so U is the thing that we're going to apply the projection to. So I write it in terms of something in U and something in U perp, like this. And then when I apply PU to the left side, I get, and we just extract the part that's in U from the right side. And ta-da, look at that. So P sub U fixes anything that started in U. And then this also immediately implies that the range of PU is contained in U, because we only ever take the thing that's in U as the output. So the output is always in U. So proof by duh, sort of. Proof by staring, how's that? And then the reverse definition, right, or sorry, inclusion right here is automatic by the definition, and so they are equal. And then for part C, it's actually kind of similar. So let's see. So if we take W from U perp, then this looks like something from U, namely 0, plus something from U perp, namely W itself. And so then when we apply the projection to W, then we extract the part of the decomposition that's in U, and so then that gives us 0. So that just tells us that PU kills anything in U perp. And of course that also implies that since it kills anything in U perp is in the null space. Now for the reverse inclusion here, if V is in the null space of the projection, then that means that V looks like 0 plus, and then the thing that goes in here has to be in U perp, right? But in order to make this equality true, the thing that has to go in the box is V itself. And so then we have V is in U perp. So that shows that the reverse containment. All right, so we've got both containments, and so we've got equality. All right, that's enough for this clip. We'll finish off the rest in the next one.